we'll start off and we'll define our ETC source and scene for whatever target that you're interested in observing. Then you'll want to specify your detector and instrument setup. Remember that we are simultaneously observing in the short wavelength and the long wavelength, so you'll want to do the setup for both short and long wavelengths. You'll next want to check for short wavelength saturation to make sure that you are not hitting up saturation. Once you know that you are not saturating the short wavelengths, you also want to check for data excess. And then once we are satisfying the data excess requirements, we also want to make sure that we're not saturating at long wavelengths. And amongst these checks, it's possible that we might need to iterate in these steps to make sure that we are balancing the saturation, SNR, and data excess. And if you'd like an overview of ETC, there are some tutorials that are available on JDocs if you need a refresher. Also, just as a reminder, when we are balancing the saturation and the signal to noise in the short wavelength, we're going to want to be able, and the data excess as well, we're going to want to be doing these trade-off with different sub-apertures, as Aaron described. And the recipe for selecting our sub-apertures, just to set it out front here, is we'll want to check the saturation in the brightest spectrum with a rapid readout mode and 2 groups per integration in the short wavelength. With this setup, we want to make sure that we are satisfying the data excess and whether or not we'll be saturating in the long wavelength. And then once you select your readout pattern to not saturate in the long wavelength, we want to go back and make sure that we're getting adequate SNR in the short wavelength. And again, the name of the game here is that we are going to be trading the sub-apertures that we choose against the readout modes that we select in order to balance out the data excess, the short wavelength SNR, and the long wavelength saturation. So let's step through this workflow for a given example. And we're going to start off by defining our source and scene. For example here, let's go through if we wanted to set up a NIRCam short wavelength DHS observation for HG 209.458b. So we'll set up our ETC notebook. We'll select the source and scene for our target. In this case, it's HG 209.458b. We can see a little scene sketch here. Things look okay. All right, once we've got that done, we want to specify our instrument and detector setup. So remember, we'll need to do this for both the short wavelength and the long wavelength. So let's start with the short wavelength. So we'll go over to the Calculations tab, select our instrument, which is NIRCam, and then go to the short wavelength Grism time series observing mode. Then we want to go over to the instrument setup, and we want to specify what that setup is going to be. The options that we have are the PSF type. Remember that we have choices for our DHS sub-apertures 2, 4, 8 spectra. The Grism that we want to select, there's only one option here, that's DHS 0 degrees. And then we want to select our filter. In this example, we're using the F150W2 filter. Just as a reminder, in our workflow, we want to actually check saturation first. So when we're in the instrument setup tab and selecting our PSF type, before we pick 2, 4, 8 spectra, we just want to start off by picking the brightest spectrum as our PSF type to check the short wavelength saturation. And then once you're done there, you want to go over to the detector tab and select your subarray. We're just going to select the subarray sub 40 stripe 1. Just as a disclaimer here, the subarray names are different for the DHS modes in ETC and APT. So if we're picking 2 sub-apertures to read out DHS spectra 4 and 7, the names that you'll see in the ETC are shown here on the orange. And this differs from the name of the subarray that you would see in APT, and those names that appear in the APT are shown in green here. This difference in the naming is temporary, but just as a heads up, the 2, 4, and 8 spectra option have these differences in the naming conventions. Okay, once you set up your instrument and detector setup for the short wavelength, we then want to go ahead and check short wavelength saturation. So in our detector setup, we selected our subarray, and then we just want to check the saturation first by selecting a rapid readout pattern and 2 groups per integration. And then we want to hit calculate and run this ETC calculation. When we do this, things look okay, but you will get a warning. The warning is because this mode is available as a shared risk, as Aaron mentioned earlier. So we're still calibrating this mode, and it's possible that the calculations and estimates that you get from ETC won't match up with your observations just yet because we're still working on refining the calibration. So that's just the heads up, something that might pop up in ETC. Okay, now that we've checked for the short wavelength saturation in this example, let's now go ahead and check for the data excess. So there are a couple of different ways to do this, but essentially what we want to use is something like this table, which helps us find readout patterns for which the full exposure time that we have in ETC is shorter than the time to reach the 5 GB limit shown here in the yellow. If it's not feasible for your to find a readout pattern for which you satisfy this criteria and your full exposure time is shorter than what you see in this yellow column, you can then move over to this time to reach 15 GB column and see if you can fit your observation with a readout pattern that satisfies this. If you can also not satisfy this 15 GB limit, then the observation is not feasible. And just as a note, this bright readout pattern is not going to be typically used for exoplanet transits. We'll probably be focusing on these DHS-N modes that Aaron described earlier for exoplanet observations. Okay, once we've checked for data excess and made sure that we are satisfying that criteria, we want to then go ahead and check for long wavelength saturation. So in order to do this, we'll have to set up another ETC calculation for the long wavelength. So we'll go to our calculation tab, select the long wavelength Grism time series, and then we'll want to go ahead into the instrument setup tab, select our filter, and then we want to select in our detector setup, the smallest DHS subarray. So that's the sub 40 stripe 1, that's for 2 spectra. And then we want to make sure that the rest of our detector setup, like our readout mode, matches our short wavelength. So in this case, we're going to select rapid readout mode, and then we want to select our number of groups per integration. And the way that we select the number of groups per integration in order to check for the long wavelength saturation goes back to this table that I showed earlier. So, and the way that we want to do this is we want to start from the bottom of this table. So we start with the readout pattern for DHS7. And the recommended number of groups per integration is 8. And so we try that first. We select 8 groups per integration and run our ETC calculation for the long wavelength Grism spectroscopy. In this example for HD 209458b, it did not saturate in the long wavelength with 8 groups. So we have no warnings and things look good to go. If you do end up having an issue where you have long wavelength saturation, we'll need to do some iteration between these steps in order to make sure that we can get our observations set up in a way so that we're satisfying these criteria and not saturating in the long wavelength and the short wavelength. Just as an example for how this iteration might go through, here's an example of running through the ETC for the long wavelength calculation for another target, for which if we do go through and start off and select the long wavelength observation to have 8 groups per integration, we end up with saturation with the 8 groups. And so in this case, the 8 groups saturates, but we can go up the rows in this table and keep trying. So if DHS 7 saturates with 8 groups per integration, then we can go up 1 row, try DHS 6 with 7 groups per integration, and so on until we run an ETC and the calculation does not saturate. So for this example, we find that for this target, 8 groups per integration saturates, but if we run the calculation with 5 groups per integration, then it does not. So that's kind of the exercise that you'll want to go through as you iterate over and check the long wavelength saturation. If you can satisfy these criteria, there's other ways that you can iterate and check your observations to design your observations to be optimal for your science needs. And another one of the ways that you can do this workflow and iterate is to repeat this workflow for larger subarrays. So previously we were just focusing on the 2-spectra subarray, the sub 40S1, but we can also take this bigger table that Aaron showed earlier and for a larger array of exposure patterns and look up the data access rate for 2-4 or the 2-8 spectra options in order to kind of set up our ETC observations. And this table will come in handy, and I'll show it again later on, but this is really what you're going to be looking at when checking your workflow for larger subarrays. So just to recap what the strategy is when going through the long wavelength saturation checks in the ETC, we'll want to configure our source and scene for our target. Then we'll set up the long wavelength Grism time series calculation. And then for the detector setup, we'll select the smallest subarray. In this case, it's the sub 40 stripe 1 short-living Grism subarray. Then we'll select a rapid readout pattern, set the number of integrations to 1. And then we want to set our groups per integration to the value in that right-hand column in the table that I showed in the slide earlier, starting with the bottom row for DHS7 readout or 8 groups per integration. We'll start with 8 groups per integration and run the ETC calculation. If your source doesn't saturate, you're good to go. The observation is feasible. But if you do face saturation with 8 groups per integration, then we can go up a row in the table, use a shorter readout pattern based on the number of groups per integration for that shorter readout pattern, and rerun your calculation. And keep going up a row until you find a readout pattern and a number of groups per integration that works and doesn't saturate. If you go through the full table and all of the potential readout patterns cause your observation to saturate, then the observation isn't feasible. But if your observation is feasible with DHS7 or any of the other smaller other readout patterns, then you might want to consider larger subarrays. So that is an overview of that long wavelength saturation check workflow. Just as a reminder, target acquisition is really important for Grism time series observations. We've linked the JDocs page here so you can overview this if you need a refresher.